All right, good afternoon. Let's start lecture, okay? I have a one-page handout, so that's for the common filter. Basically, it's the invitation of the common filter, which we'll probably start covering today. Okay? So I'm running a little bit behind this year. I only have 4 lectures left. So here's my plan, basically. So to cover the common filter, and also in order for you to be able to implement, and I need to finish a little bit review on the probability and the statistic concept, and then to go over the derivation, briefly go over the derivation of a common filter, and then come up with that basically the solution, which is the one-page handout. Okay, so that essentially is the implementation that you needed for the common filter. And then after that, I will, within the class, and go over how to implement the common filter using Simulink. So that typically needs probably 1.5 lecture according to the past experience. So we basically build things together, and then hopefully it'll work right away. And you can use that results to implement it in the project. Yes. Pardon me? Yeah, maybe we don't have time for that, right? So this year we're running late, but I really want you to kind of get understanding of how common filter works, even though you don't have to have a full understanding of sometimes the theories behind. But I want to give you a bigger picture set here, okay? Yeah, as much as possible. So that's the plan. So if I finish this today, let's say get on the MATLAB on Thursday, and then a little bit to next Tuesday. So the LQG itself is actually not very complicated. It's basically common filter plus LQR. That's LQG. Okay. So that's the plan. Then the last lecture we can have a little bit of freedom and here either do a review or whatever, right? Yeah. So I don't want to rush too much. And to give you some time for the project, basically. Okay, so that's why in the past when I do the review for the probability and statistics, I have used handwriting, but I think I'm gonna just kind of use my PDF file here to go over it. Yes.
Did you also post times that we could go into the lab?
No, I didn't post any time. You don't need the time.
Okay.
Yeah.
The next one is done, so you can go in.
That's right. Yes, right now it's done. Previously, I said a few days. Just don't go within the math labs. Yeah. Okay. Just knock on the door and let the technician know that you are from this class, and then they should let you stay. All 3 stations are on the table now. They all should be running okay. And one of the station, the one with the inverted pendulum, I copied a template in that computer, so you can copy that from that computer to the other 2 computers if using the other 2s. Okay. Yeah. There is a folder under 2017 winter in the computer with the inverted pendulum. It's okay? Yeah. But you should get on the simulation as soon as possible, though, right? You should need to get the simulation work, and then you go implement it. Because once your simulation works, it doesn't take you more than an hour or something to implement. It's very straightforward. Okay. Yeah. Okay. So let's do some quick reviews on probability and statistics. Okay, some of the concept here, it shouldn't be new to electrical students, but some of them may be new to mechanical students. Okay, for mechanical, you have only taken 1 probability course, which is the 254. Okay, and for electrical, you have taken 2. Right? Yeah. First for the concept of random variable. Okay. So random variable is a real function of this symbol zeta here, and the zeta we call that, basically called it outcome of a certain sample space. Okay, so that's basically indicated as a random variable here. So to give you a very simple example here. So, for example, let's say you're tossing let's say you're tossing a coin 3 times, okay, for each experiment. So then you can basically look at the 3 times. Okay, so the possibility is basically head, 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 or tail, head, head, right? So it depends on how the coin fall on the table. Okay, so now you can see, okay, the outcomes. So the outcomes are, so what's the outcomes of this what's the possible outcomes for this experiment? Is okay, so the possible outcome could be, I use a S for the set of outcome here. So it can be H, 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 head, 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 or head, head, tail, right? And or it could be tail, 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 right? Yeah. And if you list all the possibilities over here, and there are basically 8 outcomes here. Okay, there are 8 outcomes. So this one S that here is called the sample space. Okay, this is called the sample space here. Now, based on this experiment, then I can see, okay, so let's let capital X, which is the so-called random variable right here, so let it be the number of heads. Okay, so let's let this random variable be the number of heads. So then you, in terms of description, say, okay, then you say, okay, X is the random variable, which is basically a function. It's a function of the outcome at here, right? So, for example, see X, one of the outcome here is H, 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 right? That's one possible outcome. If I'm saying let X be the number of heads, then when you fit this outcome or this variable to this function, then the function will spit out the results. Then based on this definition, it spits out what? 3, right? Yeah. So that's the number of heads. There's 3 here. So that's how you establish this concept of random variable here. Okay. So if you HHT, then you get a 2 at here. Okay. So now probability basically means, for example, what is the probability for this random variable to be 2? Right? What's the probability for the random variable to be 2? Based on this experiment at here. Okay. So how do I do that? Then I look at all the possible outcome in here, and the probability for X to be 2. Maybe I should say, yeah, to be 2, exactly to be 2. So what's the outcome here containing 2 heads? It could be HHT. It could be what? HTH. It could also be P tail HH, right? Yeah. So each one of the outcome has a probability of how much? 1/8. So then in total, you get 3/8. So that gives you the probability for this random variable to be 2 is 3/8. Okay, so that's simple concept, random variable here. Okay, yeah. So just want to jog your mind of what random variable here is. Okay, so now everything else concepts are all evolved around random variable. Okay, and later we'll have a random vector. Okay, so it's a vector of random variables. Right. So coming back to the review at here. So this is basically really nothing new now. It's just to sort of jog your mind here. You have those materials. Okay. First simple concept is so-called expected value. So expected value, and often in time we call it the mean, right? I listed always 2 different scenarios. One is when the random variable is discrete. One is when it's continuous. Okay, so you have 2 different basically formulas, right, for discrete and continuous random variables. Okay, yeah. And in our particular case, later when we do the common filter design, we're dealing with a discrete random variable because we're talking about discrete state space model here. Okay. Okay, so that's the definition of mean value or expected value, right? So chances are this is probably what we're going to use. Actually, we're not going to dive too much into all the concept here. And then some properties, basically, if you have a addition of 2 random variables, then expected value is just addition of the 2 expected value. Okay, and same thing like this things here. Okay. Yeah. And the other property, the other statistic regarding random variable is basically the so-called variance, right? This is the variance. And here I give you the definition of variance for discrete and also for the continuous random variable. Okay, yeah. So variance is the concept basically is how dispersed, right, for the distribution of this random variable. You know, if you have a collection of data, and if you plot it out, okay, some concentrated around one value, some fairly distributed around a certain value, right? So that basically tells you the variance, right? The variance for this random variable, okay? And fx here is called the probability distribution, okay? So there's different basically probability distribution, of course, right? Okay, so that's random variable, and then you can take a look at the difference between what's the population variance, what's the sample variance. Okay, so very simple difference. Population variance basically means here's the population. This is basically nothing more than this. This is just what we have, right? This is basically 100 is the population, then 100 is the population. Okay, and a sample basically means you take a certain number of samples out of the population, right? So your population may be 1,000, but you're only sampling maybe 100 out of the 1,000 here. So that's the difference. Okay, there's a subtle difference in terms of calculation of variance when you use a population, when you use a sample. If you use a population, it's divided by the total number of the population. But if you calculate sample variance, you actually divide it by the number sample minus 1. Okay, that's a slight subtle difference at here. Okay.
Why is that?
Yeah, I was hoping you're not going to ask this question. Why is that? There's two reasons I can explain, but maybe the easiest one to explain is so if you look at this formula here, right? This is a basic calculation of sample variance. Okay, so you have xi minus the sample mean x bar at here, right? Okay. So let's say basically you have x1 and up to xn basically. Okay, this is the sample, right? And then here overall you get x bar, the sample mean. Okay, so now you can imagine, right? How do you calculate the sample mean? You basically you add them up and then you divide it by n, right? Yeah. So this one equal to x1 divided by n at here. That makes sense, right? So technically speaking, if I use x1 minus xi and then plus x2 plus x minus xi and then up to xn minus xi, I should get what? 0, right? I should get 0. So when you get this 0 at here, so you get essentially you get basically a relationship between xi and the rest of x1 to xn here, right? So you see, if you think in terms of degree freedom, so this is n degrees freedom here, isn't it, right? But then at the same time, you have one equation at here, so that eliminates actually 1 degree freedom. That makes sense, right? Because you originally you have n number samples, that's like n degree freedom here. But now you have one equation relates this, so you have eliminated 1 degree freedom here. So that's why you need to divide it by n minus. So there's only n minus 1 degree freedom basically. Yeah. And there's another reason I can let you know after class here. But as a matter of fact, you bring out how many of you taken 254 when I was teaching it? You did? Wow. You're a relic here. So if you bring out my lecture notes on that, I actually have a paragraph explaining the difference in here. Yeah. But anyway, okay. Okay, so let's go back to this review at it here. Okay. Yeah. So now let's go into this so-called joint probability. Basically, if you learn probability and statistics at third year level now, then you're learning basically of multivariable statistics, basically, right? And that's where you see the joint probability distribution. Okay. So you're taking essentially added here 2 random variables into consideration at the same time. So the idea is you can ask yourself, what is the probability, for example, for the x and the y to happen at the same time, for example? Right? So that's basically when you have multiple random variables together, right? And how do you interpret that type of probability concept here? Okay. So joint probability essentially describes that type of a scenario. Okay. If you use fx, y, and xy here, and that essentially tells you, so what's the probability for x equal to this value, for y equal to this value, right? And then you get certain probability, okay, from the probability distribution function. Okay. Yeah. Now, there's one special case which is basically is this one here. Okay, there's one special case which is this: if the 2 random variables are independent, right? Are independent, then the probability distribution function will be equal to the probability for individual random variables. Multiplying them together, then you get the joint probability, okay, distribution. Okay, so that's basically when x and y are independent here. So I'll just write down a couple more important ones here. Okay, so if x and y are independent, because what we're going to deal with a lot of situation is we have a lot of random variable, but they are actually independent. Okay. All right, so that's one thing we might need to use it just later here. Okay. Yeah. Okay. So that's independence here. And another one, actually, you will see that, okay, when we do the common filter design, is it's a symbol like this. You know, probability, a random variable b, and then vertical line, and then random variable a. Okay, yeah. So this is basically what we call the conditional probability, right? Yeah. This is a definition. This is a formula at here. So conditional probability, the idea essentially is if you know the probability for A to happen, then what is basically the probability of B, right, associated with the happening of the occurrence of the event A at here. Okay, yeah. So this is a very important actually formula for the condition for the probability, because from here, and as you actually remember, there's another one I didn't write it here. It's called the Bayes theory, okay? Bayes theory, and that's essentially based on this conditional probability concept here, right? Okay, so and a number of basically formulas associated with the conditional probability. So we can take a look at this. Okay. And continue on it here. Then, because now we're dealing with sort of a multivariable now, at least the 2 variables. Then instead of just a variance, and now we have the so-called covariance, right? The covariance at here. So covariance is a measure of how much the 2 variables change together. Okay, this is a very simple language. Okay, now I'll explain a little bit here. So how much the 2 variables are changing together at here. So for example, right? Let's say you have random variables x and y. Okay, and if I'm gonna plot it, so this is the type of things you usually will see. Let's see if this is x at here, okay, and this is y at here. Okay, so the y could be basically a distribution, something like that, maybe a Gaussian distribution, and x could be another kind of a Gaussian distribution at here. Okay, so whether these 2 random variables have a certain relationship, it's purely based on basically the observation, the plot at here. So if you plot these 2 together, you probably will see some kind of plot like this. Okay, so lots of dots, right? Lots of dots at here. Okay, So for example, let's say if you happen to have a actually linear relationship, right? That's possible, right? Your y happen to be a constant times the x. Okay? Then for this particular case, if I look at it in a planar case, okay? Let's say if k is greater than 0, okay? So then what do you see? You basically see a whole bunch of dots, okay? But these dots are more or less lined up along the straight line there, right? Yeah. So that's the idea, basically the covariance. So there might be a little bit variance at here, okay? But really depends on the relationship between the two random variables at here, right? Yeah. So the covariance essentially tells you is how much the two variables change together. If the two variables, right? So if x and y are independent. Okay, if they're independent, what does that mean? Meaning the two random variables, they are never going to change together, right? There's no relationship at all. Okay, so if you plot the relationship between the x and y, what you're going to see? You're going to see basically very random basically distributions, right? There's no patterns that you can identify at all, basically. Okay, so that's what covariance basically means at here. Okay, now in terms of the computation of the covariance, we have the formulas given over here. So this is how you calculate the covariance of the two random variables. So that's expected value of x minus its mean, and then times y minus its mean. Okay, that's how you calculate the covariance here. Okay, yeah. And this formula could be expanded, which turned out to be this one here. Okay, yeah. So and a number of properties, okay, for covariance, okay, formula. Yeah. Okay. So now the next one is the so-called correlation coefficient. So the correlation coefficient is defined as this one. So it's the covariance between x and y, and then divided by the standard deviation multiplication at here for the two random variables. Okay, yeah. Now, the correlation coefficient is a very important coefficient that actually can give you a sense of how much independency between the two random variables. So, if you look at this one here, the numerator here is what? Is a covariance, right? Is a covariance at here. Okay. So, if a covariance here equal to 0, meaning this one equal to 0, right? Or even if this is 0, then a covariance equal to 0, basically. Okay? Yeah. So if a covariance mean equal to 0, what does that mean? The two random variable must be, pardon me, independent, right? Must be independent. Okay. So that's how you can tell from this correlation coefficients at here. Okay. So let's say for this particular case, right? So if y equal to, let's say, x, okay, so it's a straight out of here, so y equal to x at here, or you just let's say y equal to kx, whatever numbers, let's say k greater than 0 again. Okay, yeah. What do you think the correlation coefficients would be? If you got basically something like this, right? And this correlation coefficient, in this case, will equal to 1, right? So there's basically complete correlation between the two random variables. Okay, yeah. And if the k is less than 0, then you got basically -1 at here. Okay, yeah. So that rho value actually tells you basically what type of sort of a variance or correlation between the two random variables at here, right? So it's very important parameters, okay, to remember. And then individually, we define basically ourselves, okay, another variable here called just the correlation. So this is basically the definition of correlation here. So the correlation is different from correlation coefficients at here. Okay, yeah. and this is a correlation in here. Okay. However, there's also a relevancy between this correlation and the independency of the two random variables. All right, yeah. So here listed a number of things. So if they're independent, then the correlation actually will be 0. Okay, it will actually be 0. The random variables are uncorrelated. Okay, if this value equal to 0. Okay, yeah. And if the two random variables are independent, they are also uncorrelated, and the covariance is 0. So independency implies uncorrelatedness, but uncorrelatedness does not necessarily imply independency. Okay, so basically, if they're independent, this term is 0. But if this term is 0, doesn't necessarily means the two random variables are independent. Okay, that's basically what this means here. Unless there's one last thing: if the two random variables are jointly Gaussian distributed, okay, then the uncorrelated, then they are basically independent. Okay, so if they are both Gaussian basically noise, and this term is 0, then they are independent. Okay. That's actually something that we're going to come back here a little bit in terms of the our system in here. Okay, yeah. So and now we're going into a little bit more sophisticated situation now. So now you have two variables, right? So now we're looking at is two random variable vectors. So x is a vector, y is also a vector here. And x contains n number of random variables. So does the y here. Okay? Yeah, so does y. I'll give you an example just shortly here. So under what scenario that we will see this basically. Okay? Yeah. So now we can still use the same concept, the covariance concept, and also the correlation concept, and apply them to this random variable vectors at here. So first of all, you can calculate the expected value for each one of the random vector at here. Okay, so calculate the random vector expected value, basically calculating the expected value for individual random variables here. Okay. And then the cross correlation, right? So cross correlation, just like the correlation between two random variable x and y, because now they're vectors here, so it's a vector multiply the transpose of the other one, and you get a matrix now basically. Okay, so you got a matrix. The diagonal matrix, so x1, y1, xn, yn, and off diagonal, right? You know, so different. Okay. Yeah. Similarly for covariance of the two random vectors. So you also get a matrix at here. Okay, so you also get a matrix. Okay. Now, what's most useful actually in our case, it's not the cross correlation and covariance at here. What's most useful for our case is actually autocorrelation and autocovariance. Okay, for our case. Okay, so here is the autocorrelation. So basically, you're calculating the correlation between the random vector itself. So basically, x transpose. So you get a matrix like this. So this matrix, as you can see, okay, diagonal is all about itself. So x1, xn, right? And then off diagonal is the x basically x1, xn, or x1, x2, right? So basically about if you remember, this is basically called the correlation, right? The correlation Rxy, as we were just defining there. Okay? And this is basically a symmetric matrix. Okay, symmetric matrix here. Okay, and then you can calculate again, and this one we can also prove that it is a positive semi-definite matrix, because if I use this matrix multiply with any vector here, we can prove that this is greater than 0. So that's why this matrix is also a positive semi-definite matrix at the same time as a symmetric matrix. Okay. Autocovariance, so you calculate the covariance between the two random variables that are here, and you plug it into the covariance formula. Okay, so you get autocovariance. And the autocovariance, you look at this one, all the diagonal here is basically the variance, right? It's the variance for individual random variable within this vector. And the off diagonal here, okay, it's the we denote that as a sigma 1n. Okay, again, this is a symmetric matrix, and this is also a positive semi-definite matrix. Okay, so that's covariance matrix. Okay. Now, under certain scenario, this autocovariance matrix and this autocorrelation matrix actually becomes the same thing. Okay, actually become the same thing. So if you look at these two matrices, this is one at here, and this is one over here, right? This is one over here. Okay. So first of all, if the mean at here, if the means at here, they are all 0, right? If the means are all 0 at here, and these two matrices, guess what? They become the same matrix, right? Become the same matrix at here. Okay. Yeah. And if the x, okay, x and y, first of all, if all of the random variables within the x are independent, okay, so basically, if you look at the x at here, what is x? X is x1 up to xn at here, right? So if xi's are independent, so none of them are sort of correlated with each other. Okay, so if you look at this covariance, autocovariance matrix, especially looking at the off diagonal one at here, right? If look at this off diagonal, so they are all independent. Then the off diagonal one at here, they're all going to be what? 0. Okay, they're all going to be 0. So this matrix at here, right, will become just the matrix here. Okay, will become just the covariance x will become simply just the diagonal matrix now. Okay, and this is actually something that particularly for our usage. Okay, yeah, because when we design our system, we will consider noise into the system now, and noise we're going to consider is a y noise, and because it's a y noise, it's a zero mean y noise. Okay, when you run each individual basically experiments, okay, each time, okay, you will have basically independency there, and the covariance of that random variable will take the format like this. Okay, yeah, good. So there's one example basically in the here I can show you one example basically illustrating this covariance concept. Okay. So in this example, where we're doing is we're taking two random basically variables s and r. Okay, so taking two random variables s and r, and we're giving it let's say s has a mean of 10, r has a mean of 20, the standard deviation for the s is 3, and the standard deviation for the r is 6. Okay, yeah. Now this is actually something you also need to know basically when you ran the certain simulation at here, or when you define certain random variables. Okay, here's how you need to define. Let's say x is taking a mean of mu, and then a standard deviation, variance of sigma. Okay, so in MATLAB, how you create this x is you would create x equal to mu plus the standard deviation, and then multiply by a MATLAB function called randn. Okay, and then you can let it generate however number of sequence you want. Okay, so generate, let's say for example 1,000 data. Okay, and the results of this one here will give you basically a Gaussian distributed random variable with mean value mu and variance of sigma square here. Okay, yeah. So this function here will generate a 0 mean and mean value of 1 Gaussian noise. Is that good? Yeah, and that's what you see in the simulation, how I generate basically S and R. Okay, standard deviation is 6, right? So generate this. Okay, and then we can plot it. We can compare. So you can MATLAB. You can use covariance command basically to compare to calculate what the variance is for the random variable itself, right? And then I can use if I create a vector S and R and then plug in a covariance, then I can calculate the covariance matrix, okay, for the two random variables that are here. Okay, so we only generate 1,000 data. You can see basically because they are both Gaussian noise. So basically means what? These two random variables must be independent, right? So if you look at the off-diagonal elements that are here, they're almost 0, right? And the diagonal elements, they are essentially the variance. If you ran it for 10,000 or even more data, it will be close to 9 and close to 36 here, right? Yeah. So that's to verify the covariance using MATLAB command right here. Okay. Yeah. And you can plot this out if you want, basically. Okay. And the plot generated basically will shows you essentially. If you look at this plot here, it's very much vertical. Like there's no inclination set here, right? So if you look at these two random variables here, which one has a bigger variance? The R value here, right? Which is this one here. So you can see here, this is basically the y-axis right here. So it has bigger variance right here, and this one has 3. So there's less variance in this direction right here. Okay. Yeah. So anyway, that's just give you some idea of this. Okay. Yeah. Okay. So and now I wanted to, instead of using that, this is basically almost getting into our purpose now here. Okay. Yeah. So the next topic here is so-called stochastic process. Yeah. So don't worry about it. You know the wording at it here. You know this is a really big topic basically. Okay. But I'm gonna just give you a very brief, very bigger picture of what stochastic process is. Okay. Actually, have you guys learned stochastic process? You learned a little bit, isn't it? Right? Yeah. Not really. Yeah. A little bit. Yeah. That's okay. So I'll give you an example right here first of all. Okay. So let's see. Here is. Okay. Here's our state space model, right? Here's state space model here. Yeah. Now, the difference is, okay, this is a very clean system. There's no noise in it, right? There's no noise. Okay. But reality is, you have the so-called process noise. So this one in here is so-called process noise. Okay. If you think of this as the description of any system, right? As a description of any system, it's a big box, black box, and you use this to describe that system in a box. Okay, and then within the system, this one here is like a noise within that system. That makes sense, right? So basically, you have something like this. Okay, so here is a system, okay. And there are white noise into the system here, right? Okay. And what we're going to happen next is, if the system has output, okay, if system has output here, then if the system output is taken by a certain sensor, then chances are you will have certain sensory noise into the system, into the measurement. Okay, so this one in here, okay, we call that sensor noise or measurement noise. And that's the two type of noises that you will see, okay, within any basically system, basically, right? Yeah. But the existence of this one, it changes significantly to the description of the system here, right? So if you think about this, okay, this is a process noise. Let's say I'm considering this is a Gaussian type of a process noise, okay? Yeah. So then every time, okay, when you ran the system, every time you ran a system here, because the existence of this random variable here, guess what? That state vector or the state variable x will also become random variable, right? Because you put a noise into this, and each time the noise will happen at a different value, right? Happen at a different value. Then the x will also take different values. It's like each time you're putting in a different input into the system, then the output of the system or the state variable calculated based on this expression will also be different now, right? So this one will also taking a different value here, okay? So this basically gives us the so-called stochastic process here. It's not like a clean system. If you fix your initial condition, every time you ran the system, what kind of expectation for the output? Same, right? That's basically what we expect is going to happen. But because of the noise out here, every time you ran a system, it's different, right? At least from the observation point of view. So this is essentially the idea here. I'm going to write, draw a few graphs here. Let's consider, okay, let's consider a stochastic process using capital X of t to illustrate this. Then this is like this. Okay. If I ran it for the first time, starting from initial condition x of 0, okay, it's the same initial condition now, then you have probably, okay, a response, okay, like this. Okay. Now this is a random variable basically, okay, yeah. And if you ran it, okay, this is essentially, let's say, trial 1. And if you ran it another time here, right, so trial 2, starting with the same initial condition, and you may see a curve which probably look like this now, right? And you can basically keep going, okay, like that. Does that make sense? Yeah. That's basically a stochastic process here, right? So if I'm interested to say, okay, so if this is t0 location, what is the value for this random variable at this t0 location, right? T0 location. As you can see, okay, here is one value, here's one value. If you keep going, so you got a whole bunch of values, isn't it, right? So at each moment, you have basically a sequence of numbers. Same thing for any other moments set here, right? Okay. So if it's not stochastic, of course, at this moment here you get the same number basically, right? But because it's stochastic, at the same moment you actually have a different basically value set here, right? Yeah. Now there's one example in my lecture actually. So let's say, for example, you know, if you are space engineers, okay, and you're interested essentially in the launching of a space shuttle and also the temperature on the surface of the space shuttle, okay, yeah. So what you could collect is, right, you could collect informations for each launch. It's like a one trial, right? At each launch you can track the temperature at a certain location, okay, throughout this launch, okay. And then based on the data you can see, okay, this is the same number, this is basically the same time at here, and this is the 175 trial. Here is the 205 trial. You see, for different trial at the same time moment, you get a different basically temperature reading at a location at here, right? Yeah. And then this overall at here at this time moment that give you a random variable basically, okay? Yeah. So in other words, technically speaking, for each moment, right, so x of t0, x of t1, for each moment they are all random variables, okay? They're all random variables. Here, here. So they're all going to be random variables here. Okay? Yeah. And that makes things quite a bit of a challenge now, basically. Okay? But you can still apply the same kind of definitions basically to the random variables that are here. So maybe you can say, okay, you can calculate what is basically the correlation between two random variables at t1 and t2, and you have basically you have the same formula. You have x as the t1, that random variable, times x at t2 transpose at that random variable here, right? So let's see if this is t1, this is t2. Okay, that's how you compare the correlations, right? And you can compare also the covariance, okay, between two random variables. So let's say I have two random variables at t1 and t1 plus, let's see, here is a difference of a tau. So t1 and t1 plus tau here. And the same formula covariance of this. One is at the t1 and the other one at t1 plus tau, right? So that's how you can derive the statistics for this stochastic process here. Okay. Yeah. Now what we're dealing with actually is simplified. Is we're trying to deal with the so-called stationary, okay, stochastic process. Okay, stationary stochastic process. So the stationary stochastic process basically means, okay, it really doesn't matter which time moment that you're gonna take at it here. So it appeared to be, here's a random variable, here's another random variable at here, right? So if I calculate the statistics, for example, the mean value at the t1 and also the mean value at the t2, and they will all be the same, basically the same mean value at here. Okay, the same mean value. In other words, the statistics of this random variable, the process, it is not going to change. Okay, it's not going to change at a different time moment at here. Okay, at a different time moment.
Is that the same as white noise stationary?
That's right. Yeah, the white noise is basically a stationary stochastic process. Yes. Okay. So, same thing. If you calculate the covariance, okay, let's say if I calculate the covariance at the t1 and the t1 plus tau, and this should be the same covariance, okay, between t1 at 0 or at tau, and you can simply use the symbol, okay, for any two random variables that's separated by an interval tau. They all have the same covariance value here. So of course, the calculation wise, right, it's capital X t minus its mean, and capital X of t plus tau minus its mean, like this, right? So that's basically the statistics property of the process do not change with time. So statistic property of the process, okay, so do not change with time. That's basically what a stationary stochastic process is. Is that good? Yeah. And interestingly, remember I was telling you a story, I was asked a question for control question during an interview, right? This is another question actually I was asked on a different occasion of the interview. This was when I interviewed at the NRC, and that NRC actually somehow, because the funding deduction was cancelled. So that the project leader asked me this question. Yeah. Honestly speaking, I have no idea what stationary process, because I didn't take when I was a graduate student, I didn't take a course in this area, right? And as you can see, I didn't find that job too, right? So everything adds up, and I end up here. Yeah, but that's the shortest answer, basically, what the stationary stochastic process is. Okay, and white noise is stationary. Okay, yeah. So I'll give you example of what white noise stationary here means here. Okay, so now let's take a look at this white noise. Okay, the white noise. Okay. Specifically, I'm looking at is a discrete, random sequence of numbers, right? Okay. So I'm going to use, say, Wn, okay, to denote this sequence set here. So n takes 0, 1, 2, okay, like this. Okay. So in other words, you have a W of 0 and W1, W2, right, and it keeps going. Is that good? Yeah. So let's say here is basically the experiment you're going to do, right? Let's see if you can experiment. If you're going to use MATLAB, whatever software you're going to generate, okay? So you're going to do experiment now. I'll do the first trial. So when you do the first trial, okay, then you generate the first sequence of numbers here, right? So I don't know what numbers that be, maybe 0.1, 0.5, and 0.3, 0.2. So that's the numbers you're going to generate, okay? Yeah, based on your defined variance, of course, okay? And then you do the trial number 2, okay? And this may be 0.2 now, 0.4, and 0.22, okay, like this. Okay, right? So you can do many trials as possible, right? Many trials. So you can trial so many, maybe 1,000 or millions, right? Whatever. Okay, yeah. But the bottom line is, when you finish the trial and you look at this data here, so what do you see? Basically, if you look at down here, down here, down here, what do you see? Each one of the column is actually what? Yeah. Yeah, but each one of the column here, basically, it's like a random variable here, right? It's a random variable here. Okay. So basically, the W0, W1, and W2, say they are all random variables. Okay, they're all random variables, and that's the Gaussian noise here. Okay, yeah, and this is actually a name they call it independent identical distribution. Okay, IID. Okay. So now what I can see doesn't matter what the n is. Okay, it doesn't matter what this n number is. So it could be 0, could be 1, could be 2. Okay, and they are all Gaussian noise. Okay, with a 0 mean and a variance of sigma square. Is that good? Yeah. And what's more here, as I think you need to write down, they're all random variables. They are all basically independent. Okay, they're all independent here. Okay, yeah. So now, if I summarize it here, and first of all, this is the overall picture here. Then, if I look at the expected value for any of the random variables that are here, they're all going to be what? 0. Right? They're all going to be 0. If I look at the cross correlation, if I look at the correlation of this random variables that are here, okay? Yeah. So what's the correlation? The correlation, as I said, it's as we just reviewed it here. I'll show you the formula. And the correlation is this one right here, okay? This one, okay? So they all have 0 mean, and they are all independent. And guess what? The off diagonal component, they're all going to be 0, right? They're all going to be 0. So if I see here, basically the writing of this one here is like what's the this one here? So what is the correlation between, for example, W0 and then W, let's say 2, for example, right? Yeah. So that's the correlation between the two random variables here, right? Yeah. Now, I put a k at here. So k basically means the difference between the two random variables at here. Okay, that's the difference in here. Okay.
Always 0, except when k is 0.
Exactly. Right. So then this one basically give us, if k is 0, then it's got to be what? The variance sigma square. If k is not 0, then you got a 0 at here, basically, right? Yeah. And to denote this thing here, we write it as sigma square times a Kronecker delta delta k, right? Yeah, and that essentially summarize this RW at here. So this RW at here, technically speaking, it's equal to expected value between W of n, any n, and n plus k at here, and transpose. Okay, yeah. So that's the correlation between these two. Okay. Is that good? Okay. So now I'm going to extend a little bit further now. Okay, one more step further. Okay, so it's just kind of keep getting it a little more complicated here. So you see, here is a white noise. So it's basically one sequence of white noise at here, right? Okay, yeah. Now, the next one here, let's look at a white random vector. Okay, it's a white random vector. So what does that mean? Basically, we define a vector, which is random vector here, right? And this vector contains n number of random variables here. Okay, yeah. And even more complicated, each one of the random variable, okay, it's actually a function of k. Okay, function of k. So if I plug k equal to 0, that's n number of random variables, right? If I k is 1, that's another set of random variables here. Okay, and of course you can keep a k up to any numbers basically. Okay, so that's called white random vector right here, and this is exactly what we're going to use for our process, right? So you see in our process right here, and we call that process noise. Okay, this is the process noise right here. Okay. So the process noise for our next study will be a white noise, and it's a white random vector right here. Good. Okay. So, and a couple of statistics, okay, are related at here. Okay, statistics related here. So I can see what is the expected value of this random vector. Okay, and how do? You're basically looking at is what's the expected value for all of the random variables inside this vector, right? And guess what? Because since we're talking about white noise, then all of them will have 0 at here. And really it doesn't matter what key value you're going to take, right? It's all going to be 0. Okay, so 0 mean white noise. Good? Yeah. And you can also calculate the correlation matrix R. Okay, so correlation matrix R. And I'll be only interested in the correlation of the matrix, okay, basically between itself. Okay, that's autocorrelation at here. Okay, so autocorrelation. And for this one here, you end up with basically a diagonal matrix. The elements of diagonal matrix is the variance for individual one of them, right? Individual. Is that good? Yeah.
Does that relate at all to the eigenvalues of
the matrix? No, no. This is just purely the variance set here, right? And this is often in time something that you will actually give. Well, if you know actual variance for the process noise, then you just plug it in here. If you don't know, then you give a good estimation, right, of here. Yeah. So that's the process noise variance essentially. Okay. Yeah. And why do I have n number of them? Because how many state vectors we have? We have, n by 1 state vectors that are here, right? And each one of them has a process noise associated with it. Okay. Yeah.
That's not the sensor.
This is not a sensor noise. Yeah, this is the process noise. Yeah. The sensor noise is we're going to come and look. So it's y equal to cx of t, x of k, and then plus that sensor noise. Okay. Yeah. Okay. So good. So I think I can stop it here. Enough, sort of enough background here. Okay, to get us started. Okay. So that's basically the next step here. So we'll look at the common filter design. Okay, common filter design. I will rewrite this linear model at here now, but as I said, the linear model this time will contain the process noise now. So here is the linear model here. Okay. As I just mentioned it here, the W is the so-called process noise, and the V is the so-called measurement noise. Okay. Or sensor noise. And now a few writings that are here. Okay, so x of k is a state which is n by 1 vector. Okay, so n by 1 vector here, and the G matrix is n by n vector again. Okay, let's see. We're talking about multi-input here. If we have r number of input, okay, to the system. Okay, so U is the control input. Suppose we have R number of input here. Then H here will be a n by R vector, right? Yeah. And Y is the output of the system. So if you have m number of output of the system, then the C at here gotta be m by n, right? N by n vector. And the process noise and the sensor noise. Okay, so the process noise is a n by 1 vector, and the sensor noise is what? So m by 1 vector here, right? Yeah. Okay. Yeah. So for W of k. Okay, for W of k, it's a vector with W1 of k and up to Wn of k. Okay. And the k can take 1, 2, okay, up to however number, right, that you are taking the measurements. Okay. Yeah. So now if you imagine, right, if you look at this writing at here, so in the back at what's running in the background here is you could have W1, 0. You could have W1, 2. You can have W2, 100. Or you may have a W, I don't know, maybe let's say 5, 200, right? You could have any, right? You know, so depends on 5 here. Maybe you have 5 states and you have this. Okay. Then all of this, right? If you look at this, every time you can run it, you can run a process. So all of this, they are all random variables here. Okay, they're all random variables. And what's more complicated is, if you think about it, if I'm gonna look at the value of x1, 0, or x2 at 150, or x4 at 10, you know. So basically whatever you want to look at it, okay?
Would those be random variables or random?
Random variables. Yeah, so they are also going to be random variables basically, right? Yeah. But these random variables are uncorrelated, right? They are basically independent, but not necessarily this one now, okay? So basically every time you run a process, you get a different number for this, right? And every time you get a different number for this, right? So things are just kind of going crazy, right? Every time you run it, okay? Yeah.
A random variable and its derivative correlated or not?
Derivative.
Yeah.
When, you
Like-
take
like
a
so
derivative.
I take the derivative of a random variable.
Yeah.
Is it correlated?
Yeah, I think so. Yeah. So if something is derived, then there got to be a certain correlation,
Like
basically.
hidden position.
Yes. Yes.
They're correlated.
Yeah. So, but bottom line is, as we said, our process noise and the measurement noise, they are white Gaussian noise. Okay. Okay. And technically, they're also zero mean. So the expected value of these two noise, okay, will be 0. Okay, will be 0 right here. And also they're independent. So if I calculate, okay, if I calculate the correlation between, you know, for example, between these two at here, they will be 0. Okay, as long as, okay, it really doesn't matter. In this case, it doesn't matter J equal to K or J not equal to K, because I'm comparing W and V at here. Okay, W and V. Yeah. And I can also calculate basically the correlation between the autocorrelation between the same random variable at here, right, for a certain K number, and now you get a so-called basically a correlation or the covariance matrix. In this case, the correlation covariance matrix becomes the same when your mean value is 0. Okay, so this one in here, and you can also calculate V and VK. Okay, you get another matrix. So these two matrices, we call that, okay, correlation or covariance matrix. Okay, covariance matrix. And this matrix is often in time that we actually will give to the system for simulation, okay, and even for implementation. Because let's, for example, you go to do the experiment and you assume there's noise in the system, right? So what type of noise? You assume it's white noise, zero mean white noise. So then you have to assume certain covariance matrix at here for the simulation or for the experiment. Okay, yeah, which I'll show you later. Okay, yeah. Okay, so basically, in short, you can write the noise, for example, is Gaussian noise with zero mean, and then with a covariance matrix over here, right? And same thing for the V at here. Okay, for the V at here, right? Yeah. So that's the same thing. Good? Yeah. So now, if I think of basically a specific, very specific example for example, for the initial value x of 0. Okay, initial value. So you're gonna essentially trying to look at what is the initial input, initial value for the system. Okay, initial value for the system. So technically, your initial value of the system is also a random noise or a random variable here. So you have the actual value at here, and then you can calculate the mean of this random variable, right? Then you can calculate basically the variance of the particular of this particular one at here. Okay, so you can run it and many times of experiment as possible, and grab the initial value, right, and calculate the mean of this. Then use this formula to calculate basically the variance or the covariance at here. Okay, so then you will have basically a matrix here. We call that, let's say, P naught matrix. Okay, and this is called covariance matrix for the X naught. Okay, for the X naught here. Good. Yeah. So as a matter of fact, for the next derivation, we will need an initial value P naught, and this is also a value that you will give to the system for the designed common filter. Okay, so it's like your initial guess. Okay, your initial guess of initial values. Okay. If your initial guess is if you think your initial guess is very much wrong, then this is basically a large matrix with a large covariance. Right? If you think your initial guess is pretty good, then you can give an initial smaller value at here for the covariance matrix. Okay, yeah. Okay, so then what's a common filter then, right? So common filter basically takes the format like this at here. It's an observer. Okay, here's your system, but bearing in mind, right now the system is a bit of a different now, right? The system has noise in it. Okay. So what we do is, we, just like regular observer design, we have our outputs, we have the input to the system, then we're going to design an observer at here. Okay, we're going to design an observer, and the observer takes both the input and output into here, okay, and spits out the estimated state vector x hat. Okay, x hat. So if there's noise in it, instead of call it observer, then we basically replace this one with the common filter at here. Okay. So this common filter basically is specifically designed to tackle the system observation when there's noise involved in the system. Okay, so if you have no noise, then you just have that full order or reduced order observer that we did in the previous lectures. If there's noise, then we need this common filter here, okay, for the observation at here. It's good? Yeah. So x hat of k is estimation of x of k. Okay, x of k here. Okay. Now, ideally, right? If you recall that, I can define the error dynamics. I can define the error of estimation as this. Right? See, that's error of estimation, isn't it? Right? Okay. What is the objective in the previous lecture for observer design? Right? When you design observer,
Get the error
to be zero, right? Yeah. So previously, you want this one to go to zero, right? You want this to go to zero here. Okay. This is a previously. Okay. Now, think about now, right? Think about now. What's the current situation? This is a noise. There's noise in it. There's also noise in it. And then you minus each other, you get something plus noise. So now this time the error, would it still possible to actually go to zero? No, not at all, right? You can't. So if you think about the white, if you have a white noise, you can never shrink it to zero, right? The noise is going to be always there, basically. Okay, so it's impossible here. So objectivity here. So objective is not to have E go to zero. Okay, it's not. Okay, that's because that's not realistic. You can't, essentially. Okay, you can't. Okay. Now this error at here, but still it's the error between the estimation at here, right? So now what we do is, okay, instead of have the error actually go to zero, so what we do is, okay, so let's calculate So I'll use the k plus 1 here. Let's calculate what? This guy here. Okay, let's calculate this guy. And the error here, because it's white noise, so we have guaranteed that the mean value of the error will be 0 for sure. Okay, so mean one will be 0. Okay, the mean of this will be 0 at here. Okay, so this is essentially what I write it here is the correlation, but when mean 0, this essentially is the covariance matrix, okay, of the error at here. Okay, the covariance matrix. So it's like this. Let's say scalar property, right? Maybe if this is scalar, maybe one estimation you end up with error distribution like this. Okay, so that's one type of error distribution, and the other one is what? Let's say maybe it's this. Okay, okay. So apparently, if you look at these two at here, which one will be better estimation? The green one, right? Because the green one has what? Less variance. Less variance. And I'm using this is a scalar. But if this is not scalar, it's a vector, then you have the writing over here, right? So then the idea is not to be bothered about whether this is going to be 0 or not. The idea is to minimize basically the variance. Try to minimize the variance at here for the estimation errors. Okay, so I define this as a matrix P. Okay, I'll define this as a matrix P at here, and this matrix P will be a diagonal basically matrix. Okay, it's going to be a diagonal matrix, and objective is to minimize this P at here. Okay, so minimize this. Minimize the P basically means you're minimizing the variance, okay, of the estimation at here. And that will ultimately get a good estimate x hat with respect to x. That make sense? Yeah. So in the next lecture, so what we're going to do is we're going to write down an expression for P, and then we'll try to derive the so-called common filter gain. Okay? Yeah. But please bring your computer. I think we can finish the derivation, get on the simulation part. Okay? So bring your computer, and then we'll start programming together. Okay?